Hi everyone, good morning from the Nelson Mandela University. It's me and my colleague, Dr. Paz here. I'm sure you can see him here. They can see you. So good morning everyone and welcome to the weekly seminar for the CoE-MaSS. This week I have the pleasure of introducing our guest speaker, Professor Gary Sharp. Professor Gary Sharp is an associate lecturer at the Nelson Mandela University, and he's been lecturing at our university for over 20 years. He has supervised various postgraduate students from master's to PhD level, including myself and Dr. Pazi over there. He has held previous position of head of department here at the Nelson Mandela University, and he's also a past president of the South African Statistical Association in 2012. He has done various work in many different fields, ranging from renewable energy to the medical field, time series analysis, and I'm sure his passion is sports statistics. Today, he'll be presenting on collaborative work that he has done in relay team selection for swimming, because he loves swimming. And with that being said, I would like to introduce Professor Gary Sharp, who will be presenting today. Thank you, everyone, and enjoy.
Morning, everyone. Chantal, thank you for a wonderful introduction there. I appreciate everything you said. Yeah, sports statistics is something I'm very passionate about, for those of you who know me. So I think you'll find this talk really up my alley, because it's something that I do like. Although I'm not much of a swimmer, I must say, but sport itself I really enjoy. I'm going to share my screen quickly, so give me a minute, please. Okay, it should be available or coming up soon enough. I'll just give it a second or two for everyone to have it on their screens. I'm going to talk kind of to the screen in front of me, so I might not look at you when I talk. Please, I apologize for that. I have a bit of a residual cough, so if I just start coughing, please also ignore that. I apologize in advance. All right, I hope you enjoy this talk, and it's actually quite coincidental that today is the start of the 2023 World Aquatics Championship in Japan. So I think this talk fits in perfectly with the time. It's actually joint work with colleagues from the University of Pretoria. I think their names are there, Prof. Inga Fabrice-Rotelli and Dr. Paul J. van Staden. They were the initiators of this project, of this research angle, and I just kind of latched on and helped them. So I think a fair amount of credit goes to them, but I'd like to build on what was originally started. The title of the talk, Optimization Algorithms for Relay Team Selection in Aquatics. I'm going to give you a series of algorithms, and we change them or we tweak them subject to the actual scenario that we're looking at. And I think that's the interesting aspect. I hope you find this interesting, and I hope you're interested in swimming, because if you are, I'm sure it will be perfectly suited to your interests. Just a bit of background so that we're all on the same page. Interest in team selection, it's gained prominence over the last few years, probably because of the IPL cricket team selection, and there's a fair amount of money involved in trying to get the best team. And there's people who've looked at trying to get the best cricketers into their team. So the prominence has grown over the last, say, 10 years, give or take. My interest started in 2006, actually a little before that, about 2004, but our first paper was published in 2006, where we used the methodology to select a cricket team. we published it in a journal which didn't really have much exposure, and it was kind of buried for a couple of years. And then we did a follow-up study in, I think, 2010, 2011, and that gained more prominence. And from then, it's been cited quite regularly. Just if you are into sport and you are a coach or a manager or whatever, in real terms, the team selection is obviously the prerogative of the person in charge of the team. That's what happens in the real world. And sometimes they don't necessarily approve of academics or analysts coming in and saying, oh, this person's stats are better than that. However, data analytics has grown recently, and more sports teams are using analytics as a tool to give them ideas and provide support and information on the team that they should look at, or individual performances. So it really is a growing area of interest. What I'm looking at today is swimming in particular, and I'm concentrating on relays in swimming. And for those of you who are familiar with swimming, you may know that there's a male and a female relay, and the predominant relay is the freestyle relay. However, a growing trend is what they call the mixed relay. So the mixed relay is where you've got men and women swimming in the same team. And the interest has grown because it's quite an exciting event to watch, because the team order changes. And sometimes if you start with your fast swimmers, you're leading by a long distance, but then the other team starts catching up. So it's become a bit more of a spectator kind of sport, which has grown, I think, the interest in swimming. I'm going to be looking at the medley relay mainly today. I'll talk a little bit about freestyles, but I'm going to focus on the medley. And in particular, I want to focus on the mixed medley relay. Just so that you know, what is a medley relay? A medley relay is one that comprises all 4 strokes, swimming strokes that are used in competitions. The backstroke, the breaststroke, butterfly, and freestyle. I've mentioned this because it's a question I sometimes used to use in a course that I taught, where I asked people to optimize a medley relay. And I had 1 or 2 people come to me and say, what is a medley? So not everyone is familiar with the term. If you are into swimming, I'm guessing you're very familiar. And if you're peripherally connected, you'll probably be aware. But there may be people who are unaware, hence a bit of background. I'm going to start right at the beginning. So something which is very, very simple. Let's have a look at a freestyle relay. In a freestyle relay, you select your 4 best swimmers. And the best swimmer is the one with the quickest time. So here's this very simple, trivial example. You've got 5 swimmers. Excuse me. There are their times. Pick your 4 best swimmers. Well, the solution is quite obvious. If you just look through the times, there's the worst time. So you're going to pick swimmer B, then you're going to pick swimmer E, then swimmer C, and swimmer D. So those will be the 4 people who make up your team. Very straightforward. So you're wondering, why do we need mathematics or analytics to worry about this? So here's, I call this example 2, the medley relay. Select the 4 best swimmers from, again, the same 5 swimmers. You can have a look. There are the freestyle times that we had on the previous slide. But now we've got times for the other strokes, backstroke, breaststroke, butterfly. So now you asked, pick the best team for the medley relay. All of a sudden, if you look here, well, maybe I must pick there, 26, that's the best time. So swimmer B must swim the freestyle. And how about butterfly? Oh, swimmer B must swim the butterfly, but I can't do that. I've got to have different people in my team. All of a sudden, the solution is less obvious. You can't just look at it and say, there's my answer. you've got to look at it a little more carefully. And this is where analytics or mathematical solutions or analysis will help. This is why a mathematical approach can be beneficial. It becomes a little easier if you just model it. So here's the data, and I just highlighted why it's not so easy. This is fictitious data. I just put it together to make it look interesting. Swimmer A has the best time for those 2 strokes. Swimmer B has the best time for those 2 strokes. And swimmer E has the second best time for all 4 strokes. So to select the team is not so easy, because who gets to swim their best times? So a nice optimization routine is useful. And this is the type of problem that I always used to set for my honors students. Give them something like this and say, go and find the solution. I might have put 6 or 7 swimmers down rather than 4, make it a little more challenging, but this is just for illustration purposes. So how would you solve this? Well, it's really quite simple. You're going to define a binary response variable, a binary decision variable, xij, as 1 or 0. 1 if the swimmer I is selected to swim stroke j, and 0 otherwise, so he's not selected. And then the time, the best time, Tij denotes as time swimmer I takes to complete stroke j. So very, very simple. You're just defining a couple of terms there. And what is your objective? Well, you want to minimize the total relay time. So you want to minimize the summation of the times your decision variables that you select. So those binary variables xij. And there's a couple of constraints that you need to be aware of. Okay. You can only select a swimmer once, so you've got to put in some sort of constraint for that. So we've just got the summation of the xij's for all of those swimmers must be less than or equal to 1. And yeah, you need to be a little careful. So you must make sure that a stroke is selected. So for stroke restrictions, constraints, you just make that summation of xij equal to 1. So this is an equality, and that's the inequality. You've got to set one of them as an equality, because if you have this as the inequality, which is our preferred way of trying to analyze integer optimization, if you don't have it as an equality, the solution will be all zeros, because remember, you're trying to minimize something. So if you set all x's to 0, minimum is going to be 0. You have to force a decision. So that ensures that you have 4 swimmers for your stroke. I'm just highlighting these now. There are sometimes problems that you need to be aware of. You can get multiple optimal solutions. In other words, more than one solution, which isn't a major problem because you've got an optimal solution, but there may be others. So be aware of it. That can play a role later on. You may have an infeasible problem. In other words, no solution is available. If that's the case, you might find that you've over-constrained the problem. So have a look at the constraints, and we'll get to something with that in a couple of minutes' time. And when you get to problems which require more variables, then you need to look at your software. To solve integer problems, integer optimization problems requires software that can do it, and can be quite pricey if you get to a lot of decision variables. To put you in the picture as to where the research frontier is, in 2020, 2 chaps, Ning and Chen, published a paper on selecting the optimal combination of a mixed 4x100 meter medley relay selection. So this is a couple of years ago. And their method, I thought, was quite clever. What they did is they used a ratio selection method. So they compared men to women in terms of the ratio, and their conclusion was that men to swim the slower strokes and women to swim the faster strokes. So it was quite that was quite an interesting idea. In 2021, they updated their research in a conference presentation where they used an optimization routine. So they developed that a little further. Then in 2022, myself and colleagues from Pretoria published a paper where we looked at trying to select the optimal age group classified freestyle relay teams for a competition. So we're selecting more than one team. We selected multiple teams for freestyle relays. And this came out the end of last year. You can have a look at it. It's a South African journal. So please feel free. So how did that grow the research? Maybe that's what you want to know. So a summary of the paper is the algorithm was to select multiple age group teams. We restricted the relays to freestyle, and we selected men's team, a women's team, and then the mixed freestyle relay team. The example that we used was a team selection for a club where there were several members who were competing at galas classified as masters events. So this differed from the Ning Chen approach in that we had multiple teams being selected. And what this really encompassed is a fair amount of increase in the dimension of the problem, obviously, but we had to redefine the objective function. That was I suppose, the key to the problem, but for all accounts. So let's have a quick look. The model, the mathematical model, we just defined our decision variables as x, I, j, k, where it's again a binary variable. One if swimmer I was selected for that age group j, and then we included for gender k, so in other words, if they were male or female, and the age groups were dependent on the event setting. TIK was just the best freestyle time for our swimmers and their particular gender. Then the objective function, which was, I think, the key to the problem. We were minimizing the time, and again, the times of the swimmers, subject to if they were selected or not, subtracted from, and this is the clever part here, this term here. This term was the national record for the age group J. So, excuse me. Because you can't compare your team to the team swimming in the lane next to you because you don't know who they are and you might not have their times, how did we go about selecting the best team, the optimal team? Well, the only possible scenario we could think was compare the team's time to the national record. And if we could minimize that distance, well, that will probably be your best possible team that you can put forward. You can't say it's better than the team next door because you don't know the team in the lane next door. But that was the way we went about it. As an example, we looked at a model, and this is the model that we used for male freestyle relay teams. So K was just set to 1. A couple of constraints that you need. Ensure that the team's cumulative ages fall within the boundaries set by the event. So masters have time categories, age categories, sorry, that they need to fall within. Obviously ensure that a male swimmer is selected for a maximum of a single team. So you can't swim for age group 1 and then age group 2 and age group 3 again. You can only swim for 1. And then you have to make sure that each team has their 4 swimmers. So those are the constraints required for selection. This is what we came up with. We defined, okay, A was the age of age group of the swimmer. LJ and UJ is just the lower and upper limit for the different groups. So the age times, if they were selected, must be greater than or equal to the lower limit for that age group. Likewise, it must be less than or equal to the upper limit. So these two constraints ensure that the categories of age group are met. And then again, that's just selecting the swimmers, and yeah, you select a 4-person team. So you set that as your equality to make sure that you have all 4. So this was the results from that particular paper. We couldn't field teams for the first 2 events, the first 2 categories, because we never had enough swimmers to fit into that age category. And perhaps I should just explain, what is this age category? That is the cumulative ages of the 4 swimmers. So they had the cumulative age got to lie between, say, 100 and 119 for the second category. In other words, you can have somebody who's 20, somebody who's 60, and another 2 20-year-olds swimming in the team. No, not 20, you'd have to have a 19-year-old to fall within that category of 119, that upper limit. But you can have people of different ages swimming together. And that's what makes it so useful. So you don't have to have everyone more or less the same age to fill into an age category. You can mix and match to get optimal teams. So for the data that we had, we found teams for 6 different categories. There were the teams, swimmers 2, 3, 5, and 10. And just for pointing out here, the cumulative age for those 4 swimmers is 157 years. And it falls within this category of 120, 159. Their cumulative time is 117 seconds. The record was 99. And what you'll see is the cumulative time is actually more than the cumulative time for the next category. That's how it sometimes works. Sometimes the younger categories have slower times. You can see that by the records as well. If you look at the records, the top category has one of the slower times of 105 seconds. So this was the work that we did last year, which came out last year. So the question is, we want to extend that freestyle methodology to select mixed medley relay teams. So I'm going to start by selecting a single team with 2 male and 2 female swimmers. I'll start simply. The constraints for that particular scenario, we need to make sure all 4 strokes are selected. You have 2 male and 2 female swimmers. No swimmer is selected more than once, and a 4-person team is selected. So we start off with our decision variables. So the example I'm going to look at, we're going to have data for 3 males and 3 females, just to keep it simple, not to be too complicated. And we want to select a team of 4 for that medley relay. We're going to define Xij as swimmer I selected for stroke J and is from gender K and 0 elsewhere. There's 6 swimmers and they need to swim one of those 4 strokes, and we've got 2 categories for our gender. Here's an example of the layout I often work with. Decision variables can be tabulated just so that you can see it. And I've got your 3 male swimmers, numbers 1 to 3. So those first 3 swimmers are male. The next 3 swimmers are the females. And that would be for stroke 1, X111 would be for the male swimmer. And you can go down through to X611 would be for stroke 1, swimmer 6. And that's last term 1 doesn't actually exist because you don't have a 6th male swimmer for our particular example, but we do have a female swimmer. And so X612 will exist, but X611 will not exist. I put it that way because I like to visualize it. And this is what it would look like if you just had it as a table. There are 12 possible scenarios, variables there, and 12 possible decision variables there. You've got a total of 24 decision variables for this particular problem. And I've got these zeros in, so it's important to be aware that sometimes you're going to have to state variables, decision variables, as zero as part of your constraints. So here's example 4. There's our decision variable. We're going to let Tijk denote the time summa I takes to complete stroke J for gender K. And what we want to do is we want to minimize the relay time, which is the summation of all their times whoever is selected to swim the stroke. So we want to minimize that summation term there. The constraints, just be aware, sometimes you need to specifically specify certain decision variables as 0. I've done it there just to show you. You've got your gender restriction, so you must have 2 males. So for k equal to 1, you're going to have 2 males, and for k equal to 2, you're going to have 2 females. So this applies to all of k. Then a swimmer is selected no more than once, so that double summation must just be less than or equal to 1 for all of your swimmers. Swimmer is only selected to swim 1 stroke, so that double summation, and here you'll see is less than or equal to 1 for all of the strokes. Excuse me. And then a 4-person team must be selected, so that summation there must equal 4. And let's have a look at a data problem. So here is the data to illustrate that methodology. Just want to quickly check something. We're okay for time, yes. Here's the 6 swimmers. Here's some times. These are fictitious data that I've just put in to demonstrate the concept. You can try and select a team by inspection. I think if you sit and look at the data for half an hour, you'll probably be able to pick the optimal team, but you're not going to look at it straight off and find it. I've just quickly used Solver in Excel to find the optimal solution. So there is my objective function. I've set up an equation in Solver. You can see all the constraints are met. Those are the inequalities. There's my stroke, there's my team. I've just ensured that all my variables are binary variables there. No problem. You can have a look at the software if you're keen. And this is the solution that I get. So my objective function, my minimum time is 106 seconds. Swimmer 1 is a male selected to swim the butterfly. That's decision variable x131. And the second male swimmer is swimming the breaststroke. The female is swimming the backstroke, and a female swimmer 6 is swimming the freestyle. So you can select a team, no problem. That's your optimal team. So can this work when selecting more than one team? So that's what we'd like to know. Conceptually, yes, the methodology will work. However, that objective function needs to be redefined. You can't just minimize the time. So the problem posed to us was, is there a methodology to select several medley relay teams to compete at masters events? The events require that the summated ages of the 4-person team fall within the age categories as defined by the rules for a masters competition. So the general form of the model, you're going to say your decision variable xijk equals 1 is swimmer I is selected for age group J to swim stroke K and is from gender category 1 or 0 otherwise, where I is the swimmer number, so NI of them, J is the age group category, NJ of them, K is the swim stroke, NK of them, and L is your gender category, NL, however many of them there are. So we want to minimize this summation, but we minimize the total time of the relay by subtracting it from, again, the record, the national record for that particular age category. That is the best way to do it, or the best way we've come up with, and it makes complete sense because you can't compare it against any other teams because you don't have that information. So we compare it or minimize it subject to the national record. The coefficient notation, just so it's all clear, TRJK, L is the swim time, RJ is the current national record for age group J, and AI is the age of the swimmer. Our constraints, we now have 5. A swimmer is selected no more than once. Each stroke is selected once per age group category. So you've got to have however many categories you've got to have as many people swimming each stroke. You have to ensure there are 4 swimmers per team. You have to ensure that each team has 2 male and 2 female swimmers. And then you have to ensure that the summative ages of the teams fall within the limits of that age group. And some of those decision variables need to be set to 0 as they don't necessarily exist. This is how you would mathematically set up those constraints. That double summation there must be less than or equal to 1 for all of I and all of J. So for all swimmers and all genders. Here's another summation, yeah, and that's for all age categories and all genders. And again, you've got a triple summation here. Your team selection must consist of 4 swimmers, and that's for all of your age groups. And then to ensure that you have your correct gender representation, you must have an equality equal to 2 there for all of your age categories and all genders. And then you've got to ensure that they fall within the limit. So you've got your lower limit and your upper limit, and that summation must fall within those categories there. And that applies to all age categories. So here is an example. So I've chosen it relatively simple. I've got 6 female swimmers, 6 male swimmers, and I want to select 2 teams. I'm going to select 2 teams for the age groups between 100 and 119 and 120 and 159. So I've got the ages and I've got times for their different events. Now this data is actual data. It's not simulated or created data. This is time from club data for people competing at masters level. What you will notice is there are gaps in this table. In other words, female swimmer 2 doesn't have a freestyle time. That's because they don't compete in the freestyle. So you don't have a time for them. So that creates the problem where you've got to set some of those decision variables equal to 0. So if you have that as a decision variable, you'd have to say, well, that must equal 0. That's one approach. So just to put it into context, the masters categories that we're looking at is these 2 categories, the age group 100 to 119. There's the national records. You can see the national record for that category is a lot slower than the next level category. This seems to be the most competitive age group between 120 and 159. You may have noticed that there's a difference in the lengths of these age groups. There it's 20 years, this is 40 years, and that's the way they are defined at master's level. There's no records for these bigger groups here, so they don't have, obviously, people to swim at that level just yet. So a couple of problems that we need to be aware of. There's no data for some swimmers and strokes. There can be multiple optimal solutions, and you can have infeasible solutions. So be aware of those. The solutions are relatively simple. The set decision variables equal to 0. What I did, I set the times to be arbitrarily high. So I penalized, instead of going and identifying each decision variable, making it 0, I just made the times of those events particularly high. So I penalized them. In other words, so that they won't be selected. It may be difficult to notice if you've got other optimal solutions, but you still have a solution that should be adequate. And then if you've got infeasible solutions, what I discovered myself is you need to see if you've got people to meet all the 8 categories, sufficient swimmers, and if the gender categories are possible, if you've got enough people for each gender category, and the combination of age and gender as well. So that can be an identifier or problem when you've got infeasible solution. So here is the analysis that I've done. Again, I just use Solver because it's quite simple. You should be able to see on the right-hand side here, team 1, the lower limit, the right-hand side lower limit is 100. My team that I ended up selecting, the collective ages is 111 years, which falls perfectly between 100 and 119. Team 2, the total years is 157, which is pretty close to that upper limit. You can see there, 2 men, 2 females selected for each team. Likewise, all the strokes selected, all the swimmers, some of them selected, some not. What you may notice here, I've got, it says 4-person team unnecessary. So I didn't actually put in that constraint of must have 4 people per team, because by putting in restrictions of male and female, 2 and 2, that ensures that I have a 4-person team anyway. So it's an unnecessary restriction. So my team that was selected from my 12 swimmers, team 1 I've highlighted here in yellow. So the first female who's swimming the freestyle, the 4th female who's swimming the backstroke, the first male will be swimming the breaststroke, and the second male will be swimming the butterfly. The second team for the next age group will be female 3, who's going to swim the backstroke, female 6, who is swimming the butterfly, and male 4s and 5s are swimming freestyle and breaststroke respectively. So what you see is the methodology does work, this is a nice simple problem. There were only 2 teams. If you've got 10 teams, it becomes a little more complicated. The conclusion, methodology is suitable for optimizing team selections. It works. The algorithms require certain adjustment depending on your scenario. For example, I didn't need to use the 4-person team, so you can always change a couple of things. And something you need to be aware of, the software limitations can be problematic. There is software, I think there's software which will solve problems with 50,000 integer variables, but they cost. They don't come cheap. So there are obviously alternative softwares that you can use, but they often have limitations on the number of decision variables that they can provide solutions for. I'd like to thank you all for listening to me. I'd like to thank the CoE-MaSS for providing this opportunity to showcase this research, which I think is very interesting and very cutting edge. To my colleagues from UP who initiated the research, I think it's quite interesting work, and I'm glad they came to me and said, hey, you're a person who's interested in sports statistics. Would you like to be involved? Thank you. And all my colleagues at NMU, Nelson Mandela University, who are always there to give me support when I need it, from a technical perspective, providing equipment and software and that type of thing. Thank you. I'm ready to take questions if there are any.
Thank you so much, Professor Sharp. So we're going to open up the floor to if anyone has any questions. You are also able to ask questions in the Zoom chat, which I have opened. I see we have a question here, Gary, in the chat box from Delene. I've never worked with solicitors. Oh, yeah, just select the chat there.
I see. Thank you, Delene. I hope you found it interesting.
Does any of our other colleagues have perhaps a question?
I can probably add, while people are thinking of something to, if they have any questions, is we initially started this work for selecting cricket teams, and then we branched out onto the swimming team selection. And I see now that there's also an opportunity to use it in athletics, where they're looking at relays, the athletics relays, because the relay in athletics, the start and the actual duration of the run gives you an opportunity to select an optimal team. So there's opportunities in that angle, in that area as well. Thank you, Warren. Yes, we've also used it for fantasy football. That is, I think I'm going to brag a little bit and say I think we were the first people in the world to try and use the idea, the methodology to select a fantasy league football team. We didn't grow on it. We kind of reached a point and then diverged. I see there's a couple of questions, Chantal.
Okay, let me just, I'm going to start off with, I didn't see who put their hand up first, so I'm going to start off with Paul van Staden.
Hi, good morning, everybody. Sorry, I'm struggling to unmute myself. Can you hear me?
Yes, we can hear you.
Okay, yeah. I apologize beforehand if there's background noise. I'm at home on leave, but when I heard Gary speaking, oh well, I have to, of course, attend, given that I'm one of the collaborators, and the other collaborator is currently in the USA, so I think it's a strange hour for her to attend. I can't remember how many hours they are ahead or before, or yeah. Gary, something that I just want to make sure again, this is a case where we only selected one team per age group. We didn't go the more complicated route of, because that is a possibility. You're allowed to have many teams within an age group. So there's a limitation we put in, if I remember correctly.
Paul, that's correct. This algorithm works for selecting one team per age group category. And the proposal I said is, once you selected one team, you can take all those people out of your database that you selected and run the routine again to select another team for possibly the same age group categories.
Yeah, we got why I'm mentioning that this is quite a interesting thing that happens, that when you are selecting these teams, and I remember when I was trying to do this myself, not using a sophisticated methods as Gary finally came up with, what often happened with me was that all the teams will end up in that popular category, and it has to do with the ages of the swimmers as well. So, and you don't want all your teams that you make be in the same category. You actually want teams swimming in the older age categories, because how it works at Master Swimming, you get points for your club where you finish. And if you put everybody in the same age category or a few age categories, then, well, you're competing with yourself and against other teams. So if you can spread your teams across the various age categories, that is beneficial. So that is part of the interesting limitations that we do have with regarding this optimization problem. Thanks, Gary. Very well presented everything.
Thanks, Paul. I appreciate it.
Okay, thank you so much, Paul. And we've got another question from Luke. Joel? If you can
Okay,
just
thank you
unmute
so
yourself.
much. Thank you, Prof, for the powerful presentation. Okay, the first thing is a request. Please, can we have the slide? I came a little late so that I can be able to follow from the beginning. Okay, the second one is the robustness of the Excel solver you are using. Okay, if we have some more variables and constraints to that model, how robust is the Excel solver you are using to solve the solution, and how long does it take to solve it?
Luke, okay, the optimization routine I used was Solver. It's an add-in for Excel. It can do up to 200 integer variables, and it does it in a couple of seconds. I've also used R just to also find solutions, to double check that I get the same answer actually. And I've done it for, I think, up to about 180 integer variables. I don't know if it goes more than that. Solver has you can actually buy the actual big package, but it costs quite a bit, and that does something like 50,000 integer variables. But I've never used it because it's a bit too expensive to buy something like that for academic research. It's, you know, it's more commercial optimization routine. And with regards to the presentation, it has been sent to the CoE-MaSS, and I would imagine they'll make it available on their website. Yes. I hope that answers your question.
Yeah, thank you, Prof.
Okay, thank you so much. Is there anyone else that would like to ask a question? Give it a few more seconds. I don't see any more online questions, Gary, and no more hands on my side. So with that in line, I'm just going to end off the session. Thank you so much, Professor Sharp, for giving us a wonderful talk on swimming. Oh, wait, we've got another question. Yay. Gary, can you see that? Any considerations of methods of handling missing data instead of filling missing observations with zeros or high numbers?
I think that's a good question, but no, I haven't. I use the high number approach as a penalty effect, just to ensure that you don't select one of those decision variables. But I haven't given it any further effect. That works. So I've got a solution.
Okay, I'll give it a few more seconds, Gary. See if anybody has a question. Okay, I'm sure if there are any questions that do come up during the day, I'm sure you welcome any emails. You can, it's gary.sharp@mandela.ac.za. And thank you again, Professor Sharp, for giving us a lovely talk. And we're looking forward to another one in the future. Thank you, everyone, for participating this Friday, and looking forward to seeing everyone again next week. Thank you, everyone.
Thank you.
Thank you. Thank you, Chantal. I appreciate everything. Thank you all for attending.